Right. So today we are going to start the nuclear energy and its uses part, which is a six subtopic under the matter radiation. So previously we learned about the radiation, radioactivity, photoelectric effect, and about X-rays, those things. So uh, under nuclear energy, I think you already know about the atomic structure, right? Atomic structure. Uh, so this first is the atomic structure. The main idea about the modern atomic structure is so there is a nucleus, positively charged nucleus at the center, and the electrons and the electron. So it's called nucleus. It's positively charged, very small, and the nucleus and the electrons. Right? So electrons orbits around this nucleus on different levels. Right? So that is the modern way, right? Modern. So this is not a 2D, 2 dimensions. In 3 dimension, you can think. So this electrons orbits around the nucleus. So that is the modern definition of this atomic structure. Actually, these neutrons. So here we have electron, and inside the nucleus. So this is called nucleus. Right. So this is called nucleus. Nucleus. So nucleus is basically made of proton and proton plus neutron. Proton plus neutron and electrons orbits around the nucleus. So more than 99% of mass is concentrated on this nucleus. That's been found. More than 99% of the mass of that atom is concentrated on the nucleus, with the addition of proton and neutron. And electrons are very lightweight atoms. So first, these neutrons were found by the scientist called James Chadwick, right? And he got the Nobel Prize as in 1935. So that's about the atomic structure. So here the symbols and charge is given. So charge of electron and proton are same in magnitude, which is 1.6 in 10 to the power minus 3 minus 19 coulomb. But the electron is negative charge and proton is positive charge and neutron is neutral. And mass of proton and neutron is almost same. And this is called the nuclear notation. So you already know about nuclear notation, which you learned in chemistry. So normally, so if we get helium atom, right? So we denote like this. So which means there are 2 electrons and 2 protons. 2 electrons and 2 protons in this atom. So this 2 represent, Z. The general notation Z is called the atomic number. The number of protons in the nucleus, whereas A represents the mass number. So mass number is the addition of the number of protons plus the neutrons, plus the neutrons. So that is easy, right? Then isotopes, right? So there are elements having same number of protons but different number of neutrons. So those are called isotopes. So here you can see when we consider these 3 uranium elements, number of protons are the same, 92, but the number of the mass number is different, right? Mass number is first one is 238, 235, and 233. So which means number of neutrons are different. So those are called isotopes, having same number of protons but different number of neutrons. Right? So then, since the mass of these atoms are very small, right? Very small. So you can see it is going 10 to the power minus 25, right? Very small values, right? So it is inappropriate to use kilogram, the basic units such as kilogram or gram to measure those, because those are very small values. And for that we have the scientists have defined unit called atomic mass unit. Unified atomic mass unit, AMU. AMU, or simply AMU, or we simply make it U. AMU or U. So that is the 1/12 of the atomic mass of carbon 612 atom. So atomic mass of carbon 612 isotope is found. It's found using spectrometer 1.99 to 6.10 to the minus 26 kilogram, and 1/12 of that is 1.66 10 to the minus 27 kilogram is equal to 1 atomic unit. So these two units are changed interchangeably. One AMU is also correct. One U is also correct. Then using the equation of Einstein's equation, mass energy equation for mass energy conversion. So we can find the energy corresponding to this 1 AMU, corresponding to atom consists having 1 AMU of mass. Right? So simply apply the values and you get 1.49 10 to the power 10 joule. Right? So then there is uh, another unit called electron volt. But electron volt uh, to address uh, the energy of atom or small particle. Because here also we can see the energy we got for 100 AMU is in the range of 10 to the power minus 10 joules. 10 to the power minus 10 joules is very small. So in order to be more convenient to be used, so the scientists have defined a unit called electron volt. So electron volt is just basically the energy required to, right? So 1 EV means the energy required to move a positive charge having 1 coulomb of uh, having 1 coulomb of charge across 1 volt. Right? So energy required to move a 1 coulomb positive charge across 1 volt, across 1 volt, across 1 volt, and that is called that is equal to electron volt. So charge of positive charge 1 coulomb, one one right, so 1 positive charge means 1 coulomb. Here it is 1 positive charge to 1 electron. So it is equal 1.6 approximately 10 to the power minus 19 coulomb. So 1.6 10 to the power 19 coulomb, and it is into voltage, because we know W is equal, the work is equal the voltage into the charge. But voltage is charge, here voltage is 1, charge is 1.6 10 to the power 19 coulomb. So 1.6 in 10 to the power 19 joule is equal to 1 electron volt. Right? So that is the energy required to move 1 electron across a 1 volt. Right? Energy required to move gained by electron. Right. So according to the mass, atomic mass unit, the electron volt can be expressed as, so this is the atomic mass unit we got. The energy consists of uh, one atomic mass unit is 1.4 into 1.49 to 39 and about minus 10, and one electron volt is that. Then the energy corresponding to one atomic mass unit is 9 931.5. 931.5 mega electron volt. So it represents mega electrons of these values. You don't have to remember these values. Just know how to do this conversion. That's enough. Uh, right. And next about in chemistry, when uh, normally when a spontaneous process happen and spontaneous chemical reaction happen, energy release. Right. So during some spontaneous process, get and plus energy. Right? During spontaneous process, the some amount of energy is released. Right. Likewise, we have chemical reactions, and like the chemical reaction, we have something called nuclear reactions as well. Right. So nuclear reactions are the reactions. So these chemical reactions are the reactions happen in between atoms. In between atoms, whereas uh, nuclear reactions are the reactions happen within the atom, within itself. Right? Chemical reactions happen in between the atoms, in between, let's say, hydrogen and helium, or sodium and chlorine. Right? Those kind of reactions are called chemical reaction, whereas nuclear reactions are some interactions happen uh, between atom itself, between a specific atom itself, inside the atom. And so those are called nuclear reaction, and those nuclear reactions are very strong. They are very strong, stronger than the chemical reaction, nuclear reactions. But and you already have this equation. Right? So nuclear reactions. That here given nuclear reaction involves the breaking or formation of strong nuclear bonds that holds protons and neutrons together in the nucleus. Nuclear reactions involve breaking or forming of nuclear bonds that holds protons and neutrons together. Right? So this happens inside the uh, nucleus. Inside the nucleus. Inside the nucleus. Inside the nucleus. These are nuclear bonds are the bonds keeping the neutrons and protons all together. So they are very strong. And from the the mass energy can equal mc squared. And so when it is found, right? So here it is observed uh, that the helium nucleus, right? We know helium nucleus is 2, 4. Helium. And so here there are 2 protons and 2 neutrons. That's it. So if we break a helium atom, helium nucleus, there are helium nucleus, without electrons. So if we break the helium nucleus, we would get 2 proton plus 2 neutrons. right? Two neutrons, two protons and two neutrons. And the mass of proton is given in atomic mass unit 1.0072676 U, and mass of neutron is given 1.0086665 U, right? So the expected value of the total mass is 2 into the mass of the proton plus 2 into mass of a neutron. The expected value of the total mass of the helium nucleus, which is this value. Uh, but when it is measured from a balance, when the mass of a helium nucleus is directly measured from a balance, the value obtained is 4.0015082. Right? So you can see which is less than 4.031882. Right? So there is a mass defect. Right? So loss of mass when converting from from the basic constituents like two protons and two neutrons to the helium nucleus. So there happens during this combination of two protons and two neutrons. The mass is not conserved during this process. That loss of mass is the difference of mass between these two values. Is 0.03. And corresponding energy difference is and so we initially found one AMU is corresponding to 931.5 mega electron volt. So by multiply 931, we get 28.3 mega electron volt. Right. So the corresponding energy difference when having this nuclear reaction. And nuclear reaction is two protons plus two neutrons is equal helium nucleus having two form. And additionally, some amount of energy is released during this nuclear reaction. Right. So during this nuclear reaction, some additional energy is released. The binding energy of the helium nucleus is 28.3. Right. So binding energy means so after the formation of the helium nucleus, right, so we have found that 28.3 energy has been lost. 28.3 mega electron volt energy has lost. So what has happened to that? So that has, so we from the mass difference we get 28.3 mega electron volt energy difference. So what has happened to that? Actually, it has been stored within the nucleus as the binding energy. Binding energy means the energy used to combine all these neutrons and protons together. Right? So that is called as binding energy. Right? So binding energy. That binding energy of this helium nucleus is 28.3 mega electron volts. So binding energy is the energy that keeps the neutrons and protons bounded together. Right? Binding energy is the energy where it is the energy where the neutrons and protons are kept together. Right? So this is another example about oxygen. So oxygen, 16 oxygen atoms. So there are 8 protons and 8 protons and 8 neutrons. 8 protons, 8 neutrons. So here also expected mass is 8 into the mass of a neutron plus 8 into the mass of proton, which is 16, around 16.12. But the true mass is measured of this oxygen 816 isotope is 15.99. Mass defect is different man is this. The binding energy is 123.83. 123.83. So here 8 protons plus 8 neutrons result oxygen 816 isotope plus energy. That energy. Right, so these are this shows a graph between the binding energy and mass number. Right, so here the binding energy per nucleon is represented as BOA. Right, so binding energy per nucleon means binding energy per nucleon. So that is the binding energy per nucleon is total binding energy that we found earlier. Here our total binding energy is 20 of helium is 28.3. Total total binding energy divided by binding energy per nucleon is total binding energy divided by total binding energy divided by the number of nucleons. Number of nucleons or total binding energy divided by number of nucleons means total number of uh, protons and neutrons, which is equal to mass number denoted by A. Mass number, right? Mass number. So that is called the binding energy per nucleon. Right? So we get the total binding energy, for example, of helium. Total binding energy is 28.3 divided by mass number is 4. At 28.3, mass number is 4. So we get 7.075. So that is the binding energy per nucleon. Right. So basically there are two types of. Next we move on to the type of nuclear reaction. So there are mainly two types. Right? Nuclear fission and nuclear fusion reactions. So mainly there are only two types of nuclear reaction: nuclear fission and nuclear fusion. So nuclear fission means uh, heavy nucleus, right? Nuclear fission means the breaking of a heavy nucleus into two lighter nucleus. Right? So it is a breaking of a very huge nuclei like X into Y and Z. Small two lightweight nucleus. But that is called nuclear fission reaction. Right? Nuclear fission is the process where heavy nucleus with mass number greater than normally 200. Heavy nucleus means mass number should be high. Greater than 200 is into lighter and more stable nucleus. Right? More stable nucleus. So here one example is given. uranium. That's first before the nuclear fission process actually first happens. This is a preliminary steps. One neutron is fallen on the uranium 92 235 atom and becomes uranium 92 236 excited one, unstable. This is unstable nucleus. So it breaks to two atoms, two nucleus, so different nucleus, barium and krypton. And in addition, the three neutrons are emitted. Plus Q represent energy. Energy, right? So here the excited or unstable uranium nucleus is broken to two more stable nuclei, barium and krypton. Right? So those type of nuclear reactions are called nuclear fission reaction. Nuclear fission reactions, actually those are the most commonly present nuclear type of nuclear reaction in Earth. But in Earth, mostly we will find nuclear fission reactions. Right? So let's see what is the reason behind that. We don't see much nuclear fusion reaction closer to Earth. Nuclear fusion is rare. Nuclear fission is more common. But so here the energy release, the amount of energy released during this above nuclear fission process is calculated. And so here another, so that is the case of this very important factor of this nuclear reaction process is it is not we cannot predict what would happen after the nuclear reaction. That's we cannot predict means the after the nuclear fission we cannot say definitely these two pair of stable nucleus would be produced, or these two would be produced likewise. So here previously in this case here after the nuclear reaction process, barium and krypton was produced. Here at same reaction. Yes, same reaction. Initially there is a uranium 135 nucleus and a neutron, highly accelerated neutron is fallen on this one. So it becomes excited uranium, unstable uranium. But here after the nuclear fission reaction, two different more stable nuclei are formed. Not the same two nucleus as the previous equation, previous reaction. Right? Right? So here, so therefore, during a nuclear reaction, different type of elements can be produced. During a nuclear reaction, not the same elements are produced, different types can be produced. So that's the important thing about this nuclear reaction. So we can predict actually what would happen after the nuclear reaction process. We cannot say definitely this would be formed. So under various conditions, different types would be formed. Different types of nuclei would be formed after the reaction. And so total energy release after 1 gram of uranium nuclei is found. Right. So here, now consider about this first equation. Consider about the first equation. And so initially there is uranium nuclei, 92 and 235 of mass number, and one highly accelerated neutron is fallen, is directed onto this uranium. That is directed onto this uranium nuclei, forming an unstable atom. Forming an unstable atom, then it get broken. Is broken to two other atoms, and in addition to that, another three neutrons are formed. Right? Another three neutrons are formed. So these three neutrons, so out of these three neutrons, one neutron might again hit. Right? So one neutron might again hit this uranium atom. So there are more uranium atoms which are not being transferred to stable atoms. So there are additional 92 and 235 isotope of uraniums. So these released neutrons from the previous nuclear fission reaction could fall on the other uranium metals which are not yet been transformed to other more stable nucleus, and that process could again happen, right? So when this neutron, so out of these three neutrons, one neutron uh, could again hit uranium nucleus which is not been transformed, then this process could happen again. Likewise, the other, so out of the three, out of these three, so one, right? So now we have three neutrons, three neutrons. So if there are uranium atoms, 235, 92, three uranium atoms, 92, and another one. So this could hit, these three neutrons could be directed onto these three other uranium atoms, and this nuclear reaction would happen continuously. Right? Could happen again. So this process could happen continuously. So those types of processes are called nuclear chain reactions. And those type of processes are called nuclear chain reactions. So here you can see initially a neutron is fallen on the uranium atom. Then fission of uranium happens. Fission of uranium, barium, and plutonium. And again, three neutrons are being formed. So these three neutrons again hit on another three uranium atoms. Then again, nuclear fission reaction happen. Another three neutrons are formed. So these three neutrons are again directed on three uranium. These three neutrons also could be directed on another three uranium atoms, nuclei. The other last three neutrons formed by this third uranium atoms, the uranium nuclei could hit on another three. So this process could happen very fast and rapidly. So those are called chain reaction. Nuclear chain reaction process was first found by this scientist Enrico Fermi. Uh, so it is very useful actually. In this nuclear chain reaction process has usages, has advantages, and both advantages and disadvantages. So we could use this nuclear chain reaction process to for good things as well as for bad things. Right? So it was first found by this scientist Enrico Fermi. A good thing is, so we can use the nuclear reaction process to produce power, energy, right? In nuclear plants, right? Nuclear plants, this nuclear reaction process is used. Right? So these are typical nuclear plants, right? Typical nuclear plants. Uh, right? Typical nuclear plants. So this is called, this is where the nuclear, so this is where the nuclear reaction happens inside this chamber, and the outside the chamber is used for the cooling, right? For the cooling process, because high energy is released and the temperature goes high during a nuclear reaction. The nuclear reactions happens inside this chamber, closely packed chamber. So another dangerous thing is if nuclear reaction, if this uh, radioactive elements go out, then it will be disaster. So care, extreme care actually. Extreme care should be taken when using these nuclear reaction processes. And so therefore, so you can see this is very tightly packed and protected from the outer surrounding. Uh, and these are called control rods. So you can see these are called control rods, and these are and this uranium nuclei are made in, right? So they are manufactured, they are uh, synthesized in the shape of cylindrical rods. Cylindrical rods. So these are cylindrical rod, uranium cylindrical rods, and these are called control rods. Right? Control rods, which are made of barium, right? Barium, boron, or the cadmium, boron or cadmium. Right? So those are called control rods, boron or cadmium. Uh, so by inserting this control rods, by inserting these controllers in between the uranium rods, this nuclear reaction process could this nuclear reaction processes could be controlled. Right? So if this is a uranium rod, so then there's another uranium rod close together, right? By inserting a controlling rod in between these two uranium rods, this nuclear reaction process. So the rate of nuclear reaction process, rate of nuclear reaction process could be controlled. Right? The rate of nuclear reaction process could be controlled uh, by using control rods. So these are called control rods. And by moving the control rod up and down, this the rate of nuclear reaction process could be uh, control rod. Control. Right? So then the heat generated by this nuclear reaction process. Right? So here the hot steam. Right? So water is heated using this nuclear, the energy gained from the nuclear reaction process. So the water becomes uh, steam. Right? So here we have water, and water is heated. So the red color means heated water. When the water is heated up, it becomes steam. It becomes steam. Uh, becomes steam, and this steam or this heated heated liquid is allowed to flow through a heat exchanger like this heat exchanger, and inside the heat exchanger another secondary uh, sodium, right? Secondary sodium liquid is allowed to flow. So then heat transformation happens during this heat exchanger. The heat would be transformed to secondary medium, and again here we have water. Here we have water. So water is pumped. Again, this is second energy exchanger, heat exchanger. This is a second heat exchanger. So again, this uh, heated up sodium, heated up sodium uh, liquid transfer energy to the cold water. Right? Then water get heated up and becomes steam. Then this steam is directed towards the turbine. So when steam hit on the turbine rotates. Turbine rotates, and this turbine is connected to the generator. Then here the electricity is produced. Right? So that is the basic principle behind this nuclear power plant. Nuclear power plant. So nuclear reaction process happens here inside this chamber. And using the control rods, the rate of nuclear reaction process could be controlled as well. And so that's a good thing about this nuclear reaction. Bad thing is atomic bomb. Right? Uncontrolled nuclear fission reaction. So if this fission reaction uh, happen in control manner using control rod, we can produce energy or what else? Nuclear power plant. There are many usages in submarines, airplanes, uh, and the spacecraft. Mostly in spacecraft, these nuclear reactors have been used because the spacecraft should travel couple of years, right? Couple of years in the space, maybe 50 years, right? So during this 50 years, the energy should be there, right? So energy should be utilized. So this nuclear reaction process, so by even very small amount of uranium atoms, small amount of uranium nucleus, uh, huge amount of energy could be produced. So that's the main advantage of this nuclear reactor by even using a very small amount of nuclear, big huge amount of energy could be produced. Then so the other one is the atomic bomb, uncontrolled nuclear fission reaction, the atomic bomb. Right. So here this process, this above chain reaction process, this process is not been controlled in an atomic bomb. It is not been controlled. So totally when it is started, it would go on continuously without any control. So it would be, you can imagine the disaster. So this is the nuclear bomb explosion. So by using a one nuclear bomb, maybe the whole most of Sri Lanka would be damaged, right, by using a one nuclear bomb. So that is very disastrous atomic bombs. So therefore, so uh, one example is the atomic bomb dropped to the Hiroshima in World War II in 1945, right? So uh, which approximately killed 130,000 people. Right? So it is said it approximately 130,000 people by one single bomb. So huge disaster. Right? So it's called nuclear bad side of nuclear. It's nuclear reactions. Right? So another nuclear hazard happened is Chernobyl. Right? In Chernobyl, a station in Ukraine in 1986. So there was in that plant there was a failure. So due to that failure, some amount of radioactive element was leaked, and it was found in Germany actually. The leakage was spread from Ukraine to Germany. But until that much of spread has happened, no one could be able to identify that. So that's the case. Yeah. It's dangerous because no one could identify until it is spread uh, across a vast region. Right? Then after finding out, there is nothing much could be done. Right? So if it could found at initial, then some protection could be done. But after the spread has happened in a vast area, then uh, there is no much solution to be done. Then the second type is, so now we know nuclear fission reaction. Nuclear fission reaction is breaking of huge unstable nuclei into two more stable nuclei. That is nuclear fission reaction. Nuclear fusion is the inverse. Nuclear fusion is the inverse of that. In nuclear fusion reaction, too lightweight. But here, lightweight. Two lightweight nuclei are bounded together and forms somewhat weighted nuclei. So here is a nuclear fusion reaction by combination of two hydrogen nuclei forms a hydrogen isotope 1,2. So those are called nuclear fusion process, nuclear fusion reaction. Combine two lightweight nuclei and form a somewhat weighted nuclei and release energy. And so here's also the energy liberation is calculated in same manner as we did before. And this is the nuclear reaction happen in sun. Right, so this is a nuclear reaction process happen in sun. That's a nuclear reaction process happened in sun. So the temperature of the core of sun is approximately very huge, 1.5 10 to the power 7 Kelvin. So most of the sun consists of hydrogen and helium. And 90% of the sun interior consists of hydrogen and helium. So it only consists very lightweight nuclei. That's why the process happened in the sun. And so by combination of hydrogen atoms, deuterium, H12 means deuterium, nuclei is formed. And by combining this helium atom, finally, so finally, electrons. Finally, helium is produced. And helium is produced. And by combining hydrogen atom, helium is produced. So this is the reaction process happened. Nuclear fusion process happened in the sun. And so this is the basic process. Nuclear fusion process. Nuclear fusion process happened in sun. Right? By combining 4 hydrogen atom, helium nuclei is formed. Helium nuclei is formed, and in addition, 2 electrons are 2 positrons. 2 positrons and energy have been released. Right? Here this main disadvantage of nuclear fusion process or fission process is the high temperature required, right, to happen. This nuclear fusion process, high temperature is required. At high temperature is required, like 1.5 10 to the power 7 Kelvin. Whereas for nuclear fission process that we discussed earlier, high temperature is not required. So that's why follow closer to the following conducting uh, closer to the conducting a nuclear fusion process is uh, impractical. So high temperature is required. High temperature is required. So therefore, not commonly used in commonly used. Not commonly, not commonly being used. Therefore, not commonly being used due to the high temperature. Due to the high temperature, this process is not being used. The nuclear fission process is much easier to implement. And so nuclear fission is what is commonly used. Right? So this is just a comparison of these two types of nuclear fission and nuclear fusion reaction process. Both of these processes emits enormous source of energy, obey Einstein mass energy conservation. So in fission, a neutron is used to start the process. Uh, in fission nuclear fission, a neutron is used to start the reaction. Uh, in fusion process, uh, high temperature is required to happen the reaction. Right? So those are the comparisons. Uh, so that's about the uh, energy or nuclear energy. Mostly we have theory part, not much equations. Just knowing what is the definition of nuclear reaction, nuclear fusion, uh, and some basic mechanism inside the nuclear reactors, the disadvantages and advantages of these nuclear reaction processes would be enough. Right? Would be enough. Then right. So next we have the fundamental constituent of matter and the interaction. Right? So fundamental uh, elements of matter, fundamental particles, elements of matter and the interaction. Right. So in ancient civilization, starting from very old age, this concept about fundamental particles were introduced. Right? So in earlier, the Chinese people believed that this physical world made of earth, metal, wood, and water. Right? Chinese people thought way back all the things, all the living things and uh, non-living one, all things are made of combination of earth, metal, and water. Right? Then by late 19th century, uh, the people believe that all the matter consists of atom. Right? And consist of atoms. Uh, as we discussed above, in atom, this is the atomic structure. There's a closely packed nucleus in between and electrons floating around the nucleus. Right? So this is the atomic structure. These are the fundamental. So here we have electrons, proton, and neutrons. The red color are neutrons. So these are electrons, protons, neutrons. All right. So initially, uh, until 19th or 20th century, it was believed that all the matters are formed of combination of electrons, neutrons, and protons. Right, neutrons and protons. And this is uh, an experiment done on that Geiger Austin experiment. So here, alpha beam is projected towards the gold foil, and most of the alpha beams would go through the most of the alpha beams would go through the gold foil, and with less deflection, they would hit this screen, fluorescent screen, which is used to capture the alpha beams. And some, as you can see here, some might be completely deflected. Right? So most of the alpha beams are just deflected a little bit and fall on the back of the gold foil, but some, rarely one or two, would deflect more. Right? So from that experiment, so here a close up of that. So this is the nuclei and these are electrons. So alpha beams are uh, directed onto this nuclei. So most of the alpha beams would travel without any deflection. Right? So alpha beams are positive charge. So when alpha beam get closer to the nucleus, it get deflected little. So when the alpha beams travels far away from the nucleus, it would not deflect it to just follow a straight line. So you can see most of the alpha rays are not deflected, but if there's alpha ray which directly comes on to the nucleus and hit on that, it would get deflected. If there's alpha ray which would directly hit on the nucleus, it would get deflected more. Right? To deflected more. So that's why this observation, right? Only couple of alpha rays are deflected. Most of the alpha rays are not deflected or partially deflected and falls on the fluorescent screen. So from this experiment, scientists, mainly the Rutherford, the experiment, he was able to find that most of the atom uh, he was able to find that most of the atom is he was able to find that most of the atom is just free space. And most of the alpha particles will pass through the gold leaf without any deflections, right? Most of the alpha particles are just pass through the gold leaf without any deflection. Some alpha particles are deflected at a small angle. Right? Some alpha particles are deflected at a small angle like this. We consider this alpha particle. So when it get closer to the nucleus, it will get deflected smaller bit. And rarely an alpha particle was deflected at an angle more than 90. But rarely means if as alpha particle comes directly onto the nucleus, it would get deflected much. Right? So from this experiment, the Rutherford identified that large amount of atom is free space. Right? Here, all these are free space. The large percentage of mass of the atom is confined to very small region in the center, and that region is positively charged. And this region is positively charged. And I think you have learned this in chemistry as well. Geiger-Marson experiment. Uh, this experiment is basically uh, done to identify the identify the nature or the nature of the uh, atomic structure. So it was proved this experiment could prove that this concept is mostly correct, right? Mostly correct. Because here we can see free space, huge free space, and only the nuclei is confined to a very small region. So mostly atom consists of free space. So this by doing this experiment, the scientists could be able to clarify that more. Yeah, clarify that more. Uh, right. Right. So earlier, these alpha beams are formed using a radioactive element. At formation of alpha beam, we discuss on the radioactivity. Uh, So these alpha beams needed to this practical. Those are being generated from a radioactive source, natural radioactive source like a lead block. Excluding that's natural radioactive source, those could be uh, generated, right? Uh, and right, so this is another phenomenon, the cosmic rays. Actually, these cosmic rays, the founding, and the study about cosmic rays. Yes, cosmic rays are uh, the high energy particles that originates from outer space and reach Earth's atmosphere. Right? Cosmic rays are very has very high energy. These alpha particles, right? This alpha particle only have uh, 5 kilo electron volt of energy. Right? 5 kilo electron volt of energy is alpha particle. It is actually small considered to cosmic rays. Right? So alpha particle consists of 5 kilo electron volt of energy, whereas these cosmic rays are high energy particles. Right? High energy particles coming from outer space and reach Earth atmosphere. Right? Reach Earth atmosphere. High energy particles come from the outer space. Right? They were first discovered by Victor Hess, 1912. Right? So here, very important observation was made. Right? Very important observation was made about cosmic rays, which are very uh, high energy particles, more than. Right? So here, Right? So their energy, this cosmic ray energy expand 10 to the power 20 electron volt. 10 to the power 20 electron. Cosmic rays has energy of 10 to the power 20 electron volt. This is equal 10 to the power 70 kilo electron volt. Right? So very huge compared to 5 electron is very huge, right? Alpha ray is only 5 kilo electron volt. This is cosmic rays are 10 to the power 17 kilo electron volt. Very huge. Right? So due to this high energy, if a cosmic ray, right? If a cosmic ray is directed, right? If a cosmic ray is directed onto a nuclei, cosmic ray onto a nuclei, if a cosmic ray is directed onto a nuclei, right? So this nuclei also could get broken. Right? This nuclei, this nucleus also could be broken. Nucleus also could be broken. Nucleus could be broken. Right? Nucleus also could be broken. So that's why, so after finding out this cosmic ray, the scientists questioned about this fundamental, earlier considered fundamental constituent. So earlier it was considered all the matters, all the things are made of electrons, proton, and neutrons. But later, after finding this cosmic rays, scientists found that these protons and neutrons also could be broken to much smaller fundamental components. These neutrons and protons also could be broken to much smaller fundamental components. So after finding out the cosmic rays, so highly energized cosmic ray falls on nuclei would break the nucleus into smaller segments. Right? So those particles are called pions, kazons, and muons. Right? So to get this much of high energy, right? So to produce cosmic ray, it is not easy task. To produce cosmic rays, there are a particle accelerator. That cosmic ray means we have to produce 10 to the 17 kilo electron volt of energy. We have to produce a particle which has 10 to the power 70, around 10 to the power 70 kilo electron volt of energy. Right? For that, we have particle accelerators. So a particle could be accelerated to very that's a particle should be accelerated to very high velocity to be a cosmic ray. So we have mainly two particle accelerator, linear accelerator and circular accelerator. Right. So linear accelerator. This is a picture of a linear accelerator and the Stanford University. Right. So which is very huge actually. The length is around 3.2 kilometers. The length of the linear accelerator. Right. So this is a linear accelerator around 3.2 kilometers. Very lengthy, right? Around 3.2 kilometers, and it is the longest linear acceleration in the world. Right? Stanford linear accelerator. So here basically there are, so this is the particle. This is the particle. And these are hollow cylindrical shaped electrode. Hollow cylindrical shaped electrode. Hollow cylindrical shaped electrode. And these electrodes are charged. So basically, so it's a hollow. Right, so there's a particle coming from here. Right, some particle. The positive particle comes from here, and when it hits this gap, so you can see there are gaps in between this hollow cylindrical uh, electrode. Right, so when when the particle hit comes to this gap, okay, so this is changed to negative charge. This electron, this is changed to positive charge. So what happens? So when this particle hits the gap, this is made negative charge, this is made positive charge. So this particle is attract. There happens, in the electrostatic field, due to this potential difference. Right? This potential difference is applied from external source. Potential difference is applied. This would be electrostatic force. Electrostatic force would be induced on the positive charge. Right? Positive charge. And then it would be accelerated and would go through this second one. Right? Second one. Second one. So here you can see, right? Here you can see the length of these electrodes are not same. The length is always higher than the previous electrode. What is the reason behind that? But length is always higher than the previous length of the electrode. That's because of the velocity. That's the velocity of the particle when going through the first electron, let's say V1, and the velocity of the particle. So, and another thing, when the particle is going through the electrode, no acceleration happens. Right? Only acceleration happens during the region where the particle flows through the gap. Here, acceleration happens. Right? Acceleration happen. Here acceleration happen. Here it is acceleration happen. Here it is here no acceleration happen. Inside this no acceleration. Inside the electrode no acceleration happen. Only the acceleration happen during this within the gap. Within the gap. Within the gap. So acceleration happen here. Okay. The reason behind isn't having a much length. The much length of electron when we move to the right side is the velocity. So velocity of third is greater than 2 and 1. Right? So when it can accelerate, the velocity becomes higher. So when the velocity becomes higher, it travels more at s equal ut. Using s equal ut, so when the velocity higher, it travels more distance during specific time period. Right? During specific time period, uh, so the length should be high. So that's why the length is high. Right? So Now these photons come to this point. But when it comes to this point, right, it comes to this point, the charge is, the potential is different. Right? So that's why an alternative current is used. Now this has been transformed to positive charge. This electron, this is negative. So when the particle would be accelerated, again the particle would be accelerated towards the uh, again the particle would be accelerated towards the again the particle would be accelerated towards the electron. Hmm. Right. So that's what happened inside a linear acceleration, linear accelerator. So to cope with this issue of having very lengthier tunnels, right? So this is a very lengthier tunnel. You can see of 3.2 kilometers. Now we have circular accelerators. At circular accelerator like this. So using a magnetic field, the mechanism is same. And the difference is now we have magnetic magnets in between these gaps. Right? So these are the gaps, and in between we have magnets. So using the magnets, yes, using the magnets, this the that the path of the particle is deviated. Right? Using magnets, path of particles are slightly deviated. Using magnets, path of particles are slightly deviated. Using magnets, path of particles are slightly deviated, and such that it is having a circular shape. So circular shape accelerators, we can construct circular shape accelerator using much less space than linear accelerators. And this is the detector. So finally, after the accelerator, finally after that, we have the accelerated particle. And this accelerated particle is the accelerated particle. That finally the accelerated particle is allowed to fall on the nucleus, this nucleus, and so this scatter some fundamental particles, more fundamental particles. And to detect those fundamental particles, we have detector like this. Right? So after this accelerated particle is collided on the nucleus to emit some fundamental particles or to detect those particles, we have detector like this. So that's how these fundamental particles are being detected. Practical. That's how it is being done. At first, this particle is accelerated using either linear accelerator or a circular accelerator. Then this accelerated particle is collided on the nucleus uh, inside the detector, and the emitted
So why do we
fundamental
use these particle accelerators?
particle accelerators. We use particle accelerators to detect the uh, fundamental constituents, right? So particle accelerator, right? So here, so go back again. So here we have alpha particle, right? So using alpha particle, when this experiment is done using alpha particles, uh, right? Some alpha particles would not. So this is a nucleus. This is the nucleus, right? So this is the nucleus, and this is the electron cloud. And these are alpha particles. These are alpha particles. Right? So alpha particles have only energy up to around 5 kilo electron volt. Right? 5 kilo electron volt. So the alpha particles travels far away from the nuclei, would not get deviated. Right? So they would just follow a straight line, and that is denoted by this middle line, dark red line. But some alpha particle which travels closer to the nuclei. So nuclei is positive, alpha particles also positive. So uh, they are get deviated, right? They are get uh, refracted a bit, and those alpha particles are these. Right? These lines represent those alpha particles, but there's a very small number of alpha particles which directly falls on nucleus. Directly falls on nucleus, which would be reflected back. Right? So those such ray alpha particle is directed by this or this. Right? So this is what happens in alpha particles. But what happens instead of alpha particles, if we direct a highly accelerated particle carrying about 10 to the power 20 amount of uh, electron volt of energy. So what happens? We accelerate without alpha particle. Uh, if we uh, accelerate particles having high energy, like 10 to the power maybe 20 electron volt. So this accelerated particles having high energy could, right? So these particles could break this nucleus as well. But here it was not happened. Right? Here it is not. When alpha particles are directed towards nucleus, the nucleus would not break. But if highly accelerated particles are directed towards a nucleus, they would break into even smaller particles. Right? So that's why. Uh, right. So here we have highly accelerated particles. So linear or circular accelerators are there to obtain these highly accelerated particles. Right? So they are just there to obtain the highly accelerated particles. So then using the highly accelerated particles, we can follow that highly accelerated particles on the nucleus, and then this nucleus could be broken into even smaller particles, more fundamental particles, and those could be detected. So basically, these linear accelerators are used to produce highly accelerated particles in order to break the nucleus of some atom and observe the fundamental particles emitted from that nucleus. Right? Basically, that is the purpose of the nuclear linear accelerator or linear or circular accelerator. Right. Uh, right. So this is a detector. This is a detector. So after doing this practical, after doing this experiment, uh, you can see this is very huge, right? Very lengthy accelerator. So after doing this experiment, scientists found more fundamental particles. Right? So these are the modern fundamental particles. Right? So we cannot say uh, these are the smallest particles yet, because the earlier scientists thought electron, proton, and neutron are the smallest particles, uh, particles that could be there, but now even smaller particles are present, are found. Right. So after doing this above experiment, scientists could found there are mainly two types of fundamental particles. Two types. Two types called fermions. Right? These are fermions and bosons. Right? Fermions and bosons. Right? So basically the fermions are the right all the living things or non-living things, all the objects uh, are made of fermions by combination of fermions. By different combination of these, there are 12 fermions. By different combination of these 12 fermions, uh, the matter is formed. And the purpose of bosons is to bind this. It is the binding particle. Right? Boson is to bind the fermions. Right? Is to bind the fermions. So the purpose of boson is to bind the fermions. Right? So here it is said bosons mediate this fundamental interaction. That bosons mediate this fundamental interaction, for example, to electrostatic charges, create an attractive or repulsive force by exchanging photons. Right? By exchanging photons, the gluon mediates the strong nuclear force, while W and Z bosons carry the weak nuclear force. So if there are positive and negative, if there are two charges, positive and negative, they would be attracted. Right? So they would be attracted by interchanging photons. So this attraction happens by interchanging photons. Right? So this attraction force between this positively charged and negatively charged element is induced using the photon. This photon. This one. Right? This one. And this one. The second one. This mediates the strong nuclear force. Strong nuclear force between neutrons and protons in a nucleus is due to this uh, gluon, gluon atoms. Gluon atoms, while weaker nuclear bonds are due to Z and W bosons. So mainly there are in the world now people have found there are only four types of forces. Right? Four fundamental forces. One is the gravitational force. There could be four fundamental forces. Gravitational force is a fundamental force. Electromagnetic force is a fundamental force, and strong nuclear force is a fundamental force, and weak nuclear force. So there are only four fundamental forces: gravitational force, electromagnetic force, strong nuclear force, or weak nuclear force. Right? So those are the four fundamental forces that present. And so then Z and W bosons are corresponding to this weak nuclear force. Gluon is corresponding to strong nuclear force. And photon is responsible for this electromagnetic forces. That the attraction force between this positive and negative charge is electromagnetic force. Electric force is electromagnetic. It is one type of electromagnetic force. Electromagnetic means electric force or magnetic force. So this electric force. So it is corresponding to electromagnetic force. And so that's the uh, that's the usage. So that's the uh, purpose of boson, to make the intermediate attraction or repulsive forces between the particles. The fermions are the basic particles. Uh, basic particles where the objects are being uh, made of, right? And there also we have two subcategories called quarks. So these six are called quarks. These six are called leptons. Quarks and leptons. So quarks we have. So the most important thing is this quarks. Quarks, up, down, charm, strange, and top bottom quarks. Under leptons we have electron. So electron is already that. So electron uh, is same. Is a fundamental. Is a fundamental uh, fundamental particle even in this uh, modern definition as well. Modern as well as previous definition. Electron is still considered as a fundamental constant, but here you can see neutron or proton. Like neutron and proton are not considered as fundamental particles now. Neutron and protons are not considered. Electron is still a fundamental, is still considered as a fundamental particle. Uh, right, so this I think you have to remember basically about these quarks. At least these quarks. So there are six quarks: up, down, charm, strange, top, bottom. That very strange names. That's however that's how are they being called by scientists: up, down, charm, strange, and top, bottom. And this is electron neutrino. P an electron is mu neutrino, muon, tau, and tau neutrino. So these are called leptons, and these are fermions. And under fermions also most important are and down. These two uh, parts, up and down. So here you can see. So this is here it is given the charge of a quark. A charge of a quark at here 2 to the power 2 over 3 is a charge of a quark with respect to electron. The particle, right? Charge of the particle with respect to the charge of electron. With respect to charge of electron, which means so here up charge of U is 2 over third of the charge of electron. Right? 2 over third of charge of electron. Charge of uh, an electron. Charge of an electron. Right? So all of these charges are noted with respect to electron. So here you can see the charge of electron is -1. Right? Here these three doesn't have any charge. This is -1, this is also -1. Electron, muon, tau. All these three have -1 charge. Up has 2 over 3, positive 2 over 3 of the charge of electron. 2 over third, here also 2 over third. Here -1 over 3. Down, strange and bottom has -1 over 3 charge. Right? And you have to know a proton. That's a proton consists of two up quarks and one down quarks. 2 up quark and 1 down quark. So proton consists 2 up quark and 1 down quark. Right? So charge of a proton. So 2 up quarks means up quark consists 2 over 3. 2 over 3 plus 2 over 3. D is minus 1 over 3. So we get 1. So charge of photon is positive 1. That is the way we already know. Right? Charge of a proton is positive 1. Charge of photon is with respect to electron, it is positive 1. Then charge of an electron is negative 1, charge of a proton is positive 1. Right? The actual value is 1.6 into 10 per minus 19 coulomb. With respect to electron, it is positive 1. The charge of photon and electron, the magnitude is same. Right? And likewise, neutron. A neutron is made of neutron is made of 1 U quark and 2 D quarks. Neutron is made of 1 U quark and 2 D quarks. UDD. 1 U quark and 2 D quarks. So charge of neutron, charge of neutron is, so U quark has 2 over 3 charge, then minus D quark has 1 over 3 minus 1 over 3, which results 0. So that is true, right? Neutron is a neutrally charge, which means 0 charge. And so we get the same result from this more fundamental particles as well. Right? So this thing you have to know. These two things, proton and neutron. Proton consists of 2 U quarks and 1 D quarks. And neutron consists of 1 U quark and 2 D quarks. And the charges. So these are these two are important. But most of the things present in world, most of things are made of a combination of U and D. Because proton and neutron are the basic, as we know, as we learned earlier. Proton and neutron are the basic fundamental components, and those two components are made of U and D. So therefore, U and D are most fundamental components of the objects or things found in Earth, and also the electron. Electron is also there. So up, down, electron. So those three are the most important fundamental components, fundamental constituents. Right, about fundamental forces, as we discussed earlier, the fundamental forces, 4 fundamental forces. So here it is given electromagnetic. Weak, strong actually is nuclear. We have gravitational force. And so there are four fundamental forces: gravitational force, electromagnetic force, and weak nuclear force. Weak nuclear force and strong nuclear force. Strong nuclear force are the strongest. So relative, if we take the strength of a strong nuclear force is 1, the electromagnetic force, the strength of the electromagnetic force relative to strong nuclear force is 1 over 100. And weak force 1 over minus 40, minus 4, minus 10 40 are the weakest. 10 to the power minus 39. Right, so strong nuclear force acts on this quarks. Right, so quarks are bounded using a strong nuclear force and electromagnetic force, between electric charges, weak nuclear force between leptons and quarks, gravitational force between masses. So range is very small for nuclear force. Nuclear force acts within a very small range. Like it is only within the nucleus, but outside the nucleus. Electromagnetic force is finite. Weak force also within a very small range. So this usage to bind protons and neutrons in the nucleus. Strong force are being utilized. Keep atoms together, electromagnetic force, radioactive decay, like beta emission, uh, happens using weak nuclear force. So gravitational force to keep the solar system together. And so that's all the theories of this section, matter and radiation. And so basically the last part, yeah, under this, under the theories we learned today, nuclear energy and its usages, mostly we have theory parts, not any equation. So you have to know what is atomic mass unit. It is the 1/12 of the mass of carbon 612 atom, and about this mass energy equivalence equal mc squared, and mass defect in nuclear binding. It's always when nuclear reaction happens, like nuclear binding happens, some amount of mass is dissipated. Mass is lost as energy. That can be found using equal mc square. And about this binding energy. But here also you have to know binding energy. About binding energy, this is somewhat important. So binding energy for nucleus is total binding energy divided by number of nucleons. Then about nuclear fission and nuclear fusion reaction. Nuclear fission is basically the breaking of highly unstable heavy nuclei into smaller, more stable nuclei. And about nuclear chain reactions, so this is the advantage of nuclear chain reaction of power plant, nuclear power plant, as well as submarine aircraft, spacecraft. Those nuclear reactors are being used to harness energy. And the bad side of as well, the atomic bomb. This the bad the bad side of this nuclear chain reaction usage of nuclear bad usage of nuclear chain reaction. Then nuclear fusion. Nuclear fusion is the combination of small lighter nuclei. Right? Combination of small lighter nuclei and forms somewhat heavy nuclei and releasing energy. So that's called as nuclear fusion. Nuclear fusion. So nuclear fusion happens in sun, basically. That's the most common place that we can see nuclear fusion, not in Earth. Right? In Earth, nuclear fusion process is rare because of high temperature. That since high temperature is required, nuclear fusion process is not commonly not common on Earth. Not common on Earth. Uh, Mostly common one is nuclear fission reaction. Thermonuclear so comparison, then fundamental I just now that's of this uh, and particles. So this is just an experiment. Right? So this particle accelerator are just to produce highly accelerated particles, and when those highly accelerated particles are directed onto a nucleus, it gets broken into smaller, even smaller fundamental particles. And when those fundamental particles are studied using this detector, they have categorized, scientists have categorized these fundamental particles. So there are 16 fundamental particles altogether here. So most fundamental particles are, although there are others as well. Most of the objects are made of up, down, and electron combination of up, down, and electron. And finally about fundamental process. For fundamental process, so nuclear force, electromagnetic, weak nuclear force, and gravitation. So about questions. Shall we try these three questions? So first one is according to the evidences found particles, matter is composed of uh, 6 quarks, 4 leptons, 6 quarks, 6 leptons. 6 quarks, 6 leptons. Matter consists of 6 quarks and 6 leptons. So bosons are just binding element. Bosons are just binding particles. Matter consists of 6 quarks and 6 leptons. The quark content of proton and neutron respectively. Proton is U, UB and UBD is neutron. What is charge of a down quark? Minus 1/3 of electron. Minus 1/3 of uh, electron. Is the charge of the quark, down quark. Right? So no much question actually. There are no any say questions from this section that we discussed today. Most of the same questions are from the first three subtopics that we discussed: radiation, radioactivity, and uh, photoelectricity. No essay question comes. Those final sections were added recently after 2019. So that's the end of this matter and radiation part as well.